All right, for workout one for lesson 25, we're going to walk through these. So first thing we know, we've got our wind turbine here. We've got the blades that are 40 meters because we have a diameter of 80 meters. So that means the radius is 40, which you can see here. And we're going to operate between 15.5 and 16.8 revolutions per minute. So for part A, we want to know the linear speed of the blade tip at max rotational speed. So we're going to look at this 16.8 RPM. So for part A, we want to know the linear speed. Here's our constants and equations. We have our handy equation right here to convert from linear, which is V, to our rotational. So that's our omega, and omega is our angular velocity or max rotational speed as seen in our question there. So in order to use this though, we need to convert omega from revolutions or rotations per minute to radians per second, because anytime we're dealing with angular, we want to be in radians per second. So down here, we need to find omega, and omega is 16.8 revolutions per minute, and we need to go to radians per second. So we know that 1 minute is 60 seconds, and we know that 1 revolution is 2 pi radians. So when we calculate all of that out, we wind up with 1.76 per second, or another way to look at that is radians per second. But radians is just a ratio, it's not an actual unit. So now that we have omega, we can find V. So V is going to be equal to R, and our radius up here, we've already said that once, is 40 meters. So we have 40 meters times our omega, which is 1.76 per second. And so our velocity is going to be 70.37 meters per second for part A. So that is the linear speed, the linear speed of the blade tip at the max rotational speed. So that's basically how fast is it going in that direction. So for part B, we want to know the radial acceleration or the centripetal acceleration at the tip of the blade at the maximum speed. So for part B, we want to know the radial acceleration or centripetal acceleration, which we've found before using our centripetal acceleration. So we can do this one of two ways. We can do it V squared over R, or R times omega squared. So we just found V, so let's just do it V squared over R. So in that case, it's just plug and chug, 70.37 meters per second. That whole thing is squared over R, which is 40 meters. And when we calculate that whole thing out, we get 123.8 meters per second squared. For the last part, the blade slows down from a maximum speed to rest in 30 seconds through how many revolutions? So we know how many revolutions does it turn. And we're looking at maximum speed. So for part C here, if we take a look at our rotational kinematic equations, so these guys here, we should see that they look very similar to our linear kinematic equations, except we plug in the rotational equivalent of our linear variables of motion. So we want to know how many revolutions, or how many angles, so to speak, we're going to rotate through. So we need something with theta in there. So that looks pretty good. We know how fast we're going, and we know how fast we're going when we stop. So we have initial and final. So we need the acceleration here. So at the beginning, we've got time. We also know beginning and end. So those two are probably what we're going to use. So if we start off, we're going to say, all right, omega final is equal to omega initial plus our angular acceleration times time. Now it's important to note that this angular acceleration is not the same as our radial acceleration or our centripetal acceleration. They are not the same thing. So we're going to have to find the angular acceleration here. So we know our final, we're coming to rest, so that's going to be 0 per second. We know our initial was at max speed, and we found that up here. So we have 1.76 radians per second plus our acceleration and 30 seconds. So if we solve that out, what we find is our angular acceleration is going to be negative 0.06 per second squared. Now that we have that acceleration, we can plug that into our other equation. So we have the final squared is equal to our initial squared plus 2 alpha delta theta. And we can plug all these in again once we know that that is 0 for our final, because we're coming to rest. Our initial is 1.76 per second. That's squared plus 2 times alpha, which we just found, which is negative 0.06 per second squared times delta theta. So that means that delta theta, when you solve it, is going to be 25.8 radians. But the question does ask us for how many revolutions does it turn. So we want to know how many complete revolutions. So we just need to convert that to revolutions. So we have 25.8 radians. And we know that 2 pi radians is 1 revolution. So we have 25.8 over 2 pi revolutions. And there's your final answer for part B.